Our customer begins their journey to modern integration by planning a migration from on-premises ACE and MQ on AIX to IBM Cloud Pak for integration, deployed on Azure Red Hat OpenShift. They are ready to follow a comprehensive guide from requirements to implementation. The journey covers architecture, deployment layout, installation, storage, high availability, security, policies, certification, foundational services, licensing, resource allocation, and node placement. Each step is crucial for a successful CP4I deployment. The customer reviews the architecture overview, learning how CP4I is structured for deployment and management on Kubernetes infrastructure, powered by Red Hat OpenShift. IBM Cloud Pak for integration deploys integration services such as MQ, App Connect, API Connect, and more on OpenShift. The customer can use UI or CLI, integrate with CI/CD pipelines, and leverage foundational services like Keycloak for identity and access management. CP4I is deployed 100% on OpenShift, with containerized components running securely using restricted SCC. Operators manage each component, and customers can install via Operator Hub or air-gapped methods, ensuring production-grade deployments. In Operator Hub, the customer finds CP4I operators and foundational services operators, ready for modular installation and management. Operators enable modular installation. Customers select only the operators needed for their use case, with dependencies managed automatically. The platform UI, identity management, and licensing operators are all part of the deployment. Once installed, operators provide APIs for custom resources. Customers declaratively create instances, and operators manage deployments, ensuring cluster configuration matches user intent. Instances or operands are the resources managed by operators. There isn't always a one-to-one relationship between custom resources and instances, making configuration flexible for complex integration needs. CP4I can be installed in all namespaces or a specific namespace, but not both. The platform UI instance count depends on the installation mode, and foundational services are installed accordingly. Operator updates are managed through catalogs and can be approved manually. Instance versions are handled separately, allowing multiple instance versions to run using a single operator version and ensuring smooth upgrades. Customers specify the instance version in the custom resource. Operators reconcile versions and available channels, with updates managed via UI or direct CR editing. Customers consider deployment layout guidance, preparing to structure their CP4I deployment for scalability and manageability. The customer asks vital questions about support models, cluster count, operator placement, namespace usage, and implications of sharing clusters between activities, all informed by best practices. There isn't a single deployment strategy for everyone. Customers weigh pros and cons to choose an approach that fits their unique requirements, leveraging OpenShift's inheritance from Kubernetes. OpenShift project isolation, user roles, operator scope, and foundational services management are considered. Namespace isolation is imperfect, and organizational structure influences deployment choices. Sharing OpenShift clusters using namespaces offers separation, but full workload isolation isn't guaranteed. Customers balance flexibility, resource efficiency, and risk. The guide provides technical background, referencing constraints and considerations that led to optimal and alternative deployment approaches. Organizational structure and technical characteristics like network isolation, resource contention, and OpenShift versioning impact deployment decisions. Operator scope, dependencies, and foundational services setup are crucial. Platform UI and access rights are managed according to cluster or namespace scope. A recommended approach is shown: separate clusters per environment, operators installed at cluster scope, and foundational services in a dedicated project. Logical groups manage deployments via namespaces. For production, deploy separate clusters for each environment. Operators are installed in all namespaces, with a single platform UI managing access across projects. Namespaces are used for logical groups, with controls for access, quotas, and network policies. Supporting items like secrets and config maps are scoped to the relevant namespaces. For non-production, clusters can be shared. Operators are installed at project scope with separate platform UI instances per project and optional shared components. Cluster sharing is common in smaller setups, with logical separation via namespaces. Constraints are considered, and operator versions are controlled per project. Each project gets its own platform UI instance. Resource-intensive components like API Connect or event streams may be shared across user domains to optimize resources. The customer prepares to obtain CP4I, reviewing options for software acquisition and entitlement management. Deployment involves preparing OpenShift clusters, installing operators, configuring image access, and deploying components. Operator Hub and Lifecycle Manager are central to installation. CP4I can be deployed through IBM Operator Catalog, Mirrored Registries, IBM Cloud Catalog, AWS Marketplace, or Azure Marketplace, each with specific capabilities and air-gap options. CP4I works on any OpenShift cluster meeting requirements, customer-installed, hosted, or network-restricted clusters. Air-gap deployments require image mirroring and policy configuration. Customers can use a 60-day trial with any OpenShift installation using a provided entitlement key. OpenShift licenses are not included in the CP4I trial. Component images are accessed from the IBM Entitled Container Registry. Customers use their entitlement key, update pull secrets, and can mirror images for offline environments. For clusters without direct registry access, images are mirrored to local registries, with image content source policies redirecting image requests. OpenShift includes its own build pipeline registry, but is not suitable for mirroring. On IBM Cloud, CP4I is installed onto OpenShift clusters with operators managed by the IBM Software Catalog. Entitlement keys are automatically handled based on the IBM Cloud account. AWS Marketplace offers templates to install both OpenShift and CP4I. All operators are installed, and the platform UI is created for cluster management. Azure Marketplace enables customers to create or use existing ARO or self-managed clusters. All CP4I operators are installed, with an instance of platform UI created for management. Storage selection is a key step. CP4I uses persistent storage for resilient state data, and customers must choose a provider based on reliability, replication, and supported features. CP4I components use a mix of block, file, and object storage, with each provider offering different benefits and trade-offs. Customers evaluate use cases for storage selection. Data access patterns include read-write-many, RWX, read-write-once, RWO, and S3 object storage. Each component's requirements determine the best type of persistent volume. CP4I does not require raw block device storage. Components using RWO provide their own replication, while S3 and RWX require provider-level replication for high availability. Customers choose between platform-provided storage, like Azure Disk or AWS EBS, and software-defined storage, such as OpenShift Data Foundation or Portworx, each with unique management characteristics. CP4I supports a range of storage providers, including OpenShift Data Foundation, IBM Spectrum Fusion, Portworx, and native cloud storage options like Azure Disk and AWS EBS. Public clouds offer built-in storage providers. Customers can use Azure Disk and Files, IBM Cloud Block and File, AWS EBS and EFS, or software-defined storage like ODF and Portworx. Cloud providers have limits on block volumes per region and per worker node. Customers must plan deployments within these constraints, especially for high availability scenarios. AWS EBS is used for RWO, EFS for RWX, and S3 for object storage. ODF and Portworx support cross-AZ replication, but performance and cost trade-offs must be considered. ODF offers cross-AZ replication and flexibility, while AWS EBS/EFS are managed by AWS with specific performance and deployment characteristics. Customers weigh operational and resource requirements. Azure Disk provides RWO, Azure Files supports RWX, and software-defined storage like ODF and Portworx offer replication and flexibility for CP4I deployments. Storage replication across availability zones is crucial for resilience. Customers choose between single AZ block storage and cross-AZ replicated file storage, depending on component-level replication. CP4I components with RWO storage provide their own replication, allowing use of single AZ block storage. Initial deployment spreads replicas across zones for resilience. Replicated storage providers like ODF and Portworx add performance overhead and cost. Customers must balance flexibility, failover, and network charges against operational needs. RWX storage relies on provider-level replication for high availability. Object storage like S3 is used for static, infrequently updated data, while file storage is used for active workloads. CP4I supports a variety of storage providers. Customers evaluate options based on replication, performance, and operational trade-offs to make informed decisions. High availability is vital for CP4I deployments. The system is configured to withstand hardware or software failures, maintaining service continuity. HA keeps systems running during failures, while DR is for recovery after catastrophic events. Recovery time and endpoint objectives are considered during planning. HA is instantaneous and autonomous, while DR requires manual intervention and may take longer. Both strategies are important for production systems. High availability is achieved by spreading nodes across failure domains, virtual machines, hosts, racks, data centers, or cloud regions and zones. Each domain offers a level of fault tolerance. OpenShift clusters are spread across multiple failure domains. Public cloud providers offer placement groups and availability sets to control node distribution for high availability. To implement HA, customers deploy OpenShift clusters across 3 failure domains, label nodes, deploy CP4I components in HA configurations, and develop capacity and disaster recovery plans. High availability starts with a resilient OpenShift cluster, then CP4I components are deployed in HA configurations, with capacity planning for service interruptions. The OpenShift control plane uses quorum-based HA, requiring at least 3 control plane nodes across failure domains. Documentation guides proper node placement for resilience. CP4I components use active-active, active-passive, or quorum-based HA. Each method requires specific node counts and failure domain distribution for effective operation. OpenShift uses Kubernetes labels to distribute workloads across failure domains, ensuring high availability for CP4I components. Administrators verify node labeling for proper scheduling. Each CP4I component uses a tailored HA approach: active, failover, quorum, or service availability. Minimum worker nodes are specified for each capability. Security begins with authentication and authorization. CP4I uses Keycloak for identity management, supporting LDAP, OIDC, SAML, and OpenShift integration. Authentication identifies users and can delegate to external providers like LDAP or Active Directory. Authorization grants permissions based on Keycloak client roles. CP4I installs Keycloak and generates an administrator password for integration admin, accessible via OpenShift console or CLI. Keycloak's built-in registry allows creation of users and service accounts. Administrators use the Keycloak console for management tasks. LDAP integration connects CP4I to enterprise directory servers, managed via Keycloak admin console, accessible from within CP4I. OIDC and SAML enable integration with enterprise identity management systems configured through the Keycloak admin console. OpenShift authentication lets users log in to CP4I using OpenShift credentials, with roles assigned via Keycloak. Authorization in CP4I is based on OpenShift RBAC and Keycloak roles, with client-level permissions for actions within components. Keycloak realms organize IAM systems, clients represent integration instances, and roles define permissions at realm and client levels. Administrators assign roles to users and groups using Keycloak's user management interface, controlling access to CP4I instances. CP4I supports validating admission policies, enabling administrators to apply requirements to cluster resources using declarative policies. Policies consist of a validating admission policy, parameter resources, and bindings. These define logic, details, and scope for enforcement. Policies are cluster-wide and can escalate privileges. Policy creation support is disabled by default in CP4I to mitigate risks. To enable policy support, run OpenShift 4.17+, use Platform UI 16.0.8+, and create appropriate cluster role and cluster role binding resources. Platform UI allows creation and editing of policies and bindings. Templates can be reused, with resources managed via form or YAML views. IBM certification ensures CP4I is secure and production-grade, with world-class Kubernetes software, consistent standards, and comprehensive testing. Before installing CP4I, customers install foundational services like Keycloak and PostgreSQL in the same installation mode as CP4I. CP4I is licensed based on VPCs, calculated from CPU limits for chargeable containers. Licensing ratios and capping schemes are applied per instance type. OpenShift uses resource requests and limits for CPU and memory to schedule pods and control runtime resource usage. Overcommitting can cause evictions if limits exceed physical resources. Node placement allows customers to control resource pools, prevent workload contention, and optimize licensing. Pods can be scheduled to dedicated nodes using project and cluster-wide selectors. Key terms include channels, custom resources, custom resource definitions, instances, operators, reconciliation, and security context constraints. Important concepts for understanding CP4I on OpenShift.